All right, guys. So in this last video lesson of Unit 7A on exponential functions, we're going to be finishing off this last objective, number 9. And our focus is going to be on applying what we know about exponential functions in regards to compound interest, so things to do with money. And we will still be talking about growth and decay models as well. So if you can join me with this last aspect. So where's my pen? There it is. Exponential applications with a focus oh, okay, on compound interest. So in finance, future values of various accounts are computed using the function f of x equals p times 1 plus r to the power of t. This is essentially like what you've been working with, where it's a times b to the power of x, where a is your initial value, it's your y-intercept or your starting point. B is your multiplier, or your growth or decay rate. That's the same thing that's here, right? So it's like, if you think about it, if something's growing at 50%, you're going to be multiplying by 1.5. So that's where the 1 plus comes in. So you've really been working with this, and then t is the amount of time. F of t is the future value. P is the present value or the principal amount. I feel like I used the wrong principal. It's okay. R is the rate of change, and T is the time. However, the interest rates are almost always tied to a specific time period and only accumulate once once that time period has elapsed, which is called compounding. So it's like you could earn interest every month, you could earn interest weekly, semi-annually, annual, like that idea. In this context, we refer to the time periods as compounding periods. A compound period is a fraction of 1 year. So our formula for compound interest is A equals P, so times 1 plus R over N to the NT. So for this one, P is still your principal, R is still your rate, N is the number of times compounded in a year. So if it's compounded monthly, your N value would be 12, right? So you can think a little bit logically through it. And then compounding continuously, so that's like it is always compounding. You're going to use it's A equals PE to the RT, where E is Euler's number, which we spoke about in an earlier lesson. So that's the one that's about like 2.71 approximately. So that's the irrational number. So that is, or this is PERT is often what it's referred to as. So if we just briefly go through these just to make sure that we're clear on what it indicates. So if you're compounding annually, compounding period, what am I going for there? I'm just going to fill in this right column. Compounding, this is 1 time. Semi-annually, 2 times. Quarterly, 4 times a year. Monthly, 12 times a year. Weekly, 52 times a year. Daily, 365 times a year. Right? We'll leave it at 365. Compounding period. So it'd be half a year, every half a year. This is every 4th a year. Monthly, 1/12. Weekly, 152. Daily, 1 over 365. This is the column that's more important, the number of times compounded per year, because this is going to be your N. All right, so let's look at some practice with this if I can locate what I did with it. So this is the last page, front and back, of this workbook. Wow, guys. Okay. So the 3 formulas at the top, you must show which formula you're using and what values you're plugging in. So Sawhill put $3,000 in a bank. That pays 12% interest, and it's compounded yearly. So that's 1 time per year. Find his balance after 20 years. So we're going to be using the formula here. I mean, it's compounding yearly, so really either one of these would technically be fine. Really, all I need to do there, though, is 1 plus r to the power of t. If I want to do the other one, that's fine. The principal amount, the initial amount, is $3,000. Your rate is 12%, so 0.12. And in this case, the t, the time we're looking at, is 20 years. And it's compounded yearly, so A equals 3,000, 1 plus 0.12 to the power of 20. And then I can go ahead and write into my calculator. It's hard for you to see, isn't it? It's okay. 3,000, 1 plus 0.12 to the power of 20. Enter. So 28,938 and 88 cents. So after 20 years, he's going to have $28,938.88. Right, which makes sense because it was growing. Maria put $7,000 in a bank. That's going to pay 2.5% interest. Compounded yearly again. Find her balance after 10 years. So again, I'm going to say A equals P times 1 plus R to the power of T. The principal amount, 7,000. R, the rate, is going to be 0.025. And then T is going to be 10. So A equals 7,000 times 1 plus 0.025 to the power of 10. So let's see. 7,000 times 1 plus 0.025 to the power of 10. So 8,960 and 51 cents. 8,960 and 59 cents. Let's see what Alfreda did. Alfreda put $10,000 in a mutual fund, and it pays 6.25% compounded yearly again. After 30 years, how much money is she going to have? So A equals P times 1 plus R to the power of T. The initial amount, the principal amount, is 10,000. The rate is 0.0625. Don't cut the decimal off. T is 30 years. She's really going to wait and see, which is good. 10,000, 1 plus 0.0625, the power of 30. What was it? 10,000 times 1 plus 0.0625 to the power of 30. 61,640 and 79 cents. 61,640 and 79 cents. Nice. It's a nice chunk. Lydia put $500 into a mutual fund and is going to pay 15% interest, also compounded yearly. Find her balance after 20 years. So A equals P times 1 plus R to the power of T. P, the amount she started with, is 500. The rate is going to be 0.15, 15%. And then T is 20 years. So A equals B 500 times 1 plus 0.15, so the power of 20. $500 times 1.15, which is 1 plus 0.15, to the power of 20. 8,183.27. Great. So for all of these, we were just using that first formula where it was compounded yearly, like at the end of the year. They were all growth, right? So it's like you could run into a situation where something depreciates. Like imagine what would you do if something was losing value? Like you bought a car, you drove it up the lot, and it lost a certain percentage. You're going to do 1 minus that rate, which is just going to be the leftover. Like that's the same thing. Like if you have buy a shirt that's on sale and it's 20% off, you're going to take it and multiply the original price by 0.8 because that's the leftover percentage, which is really coming from 1 minus it. So it's actually this formula. Let's look at a few more. So Lindsay put $3,000 into a bank. $3,000 into a bank. That pays 12% interest compounded monthly. So now we're getting to a slightly different one. How much is she get after 3 years? So I'm now going to use the formula. P times 1 plus R over N to the power of NT. Because I'm no longer just doing this annually or once a year. It's compounding monthly. So the initial amount is going to be 3,000. The rate is going to be 0.12. And the number of times it's compounded per year, well, if it's monthly, it's going to be 12. So A equals 3,000 times 1 plus 0.12 over 12 to the 12 times, what are we working with? 3. I like to multiply these before I plug them into my calculator just so I don't make a typo. So 12 times 3 is 36. So if I go ahead into my calculator, I'm going to do 3,000 times 1 plus 0.12 divided by 12 to the power of 36. Sorry, that's very hard for you guys to see. Let's see, is that any easier? I guess a little bit. So Lindsay will have 4,292. $4,292.31. Leo put $7,000 in a bank account that pays 2.5% interest compounded quarterly. What will his balance be after 5 years? So A equals P times, and again, we're not doing this annual anymore, so it's R over N to the power of NT. P is going to be 7,000. The rate of interest is 0.025. And then the time is 5. And the number of times a year, well, if it's quarterly, there's going to be 4 quarters in a year. So it's going to happen 4 times throughout the year. So A equals 7,000 times 1 plus 0.025 over 4 to the 4 times 5, which is 20. So I would choose to enter that 20 in my calculator instead. So 7,000 times 1 plus 0.025 over 4 to the power of, what did we just say that was? 20. So 7,928. And 95 cents. Aditya put $500 into a mutual fund that pays 15% compounded daily. How much money will he have after 50 years? So Aditya put $500. So again, it's compounded daily. So P times 1 plus R over N to the NT. So the principal amount, the initial amount, is $500 is how much you put in. The rate is 15%, so 0.15. The number of times, it's daily, so 365. And then we were talking about 50 years he's going to leave it in there. Let's see how much he's going to have. So 500 times 1 plus 0.15 over 365. It's the power of NT, so 365 times 50, which is, let's see, 18,250. I don't know if I remember all of this. Let's see. 500 times 1 plus 0.15 over 365 to the power of 18,250. 18,250. 90,000. No, 902,000. 629 and 48 cents. Wow. %15 interest though. If we check out the last one. So Sean put $10,000 into a mutual fund. It pays 6.2 interest compounded continuously. So the first one we're saying where it's continuous. What will his balance be after 2 years? So for something like this, you're going to use part. Okay, so P, the initial amount is 10,000. The rate is 0.0625, and the timeline we're talking about is 2 years. So A is an equal 10,000 e to the power of 0.0625 times 2. So I'm going to go ahead and multiply 0.0625 times 2. So I'm really dealing with 10,000 e to the power of 0.125. I'm going to slide that over so you guys are going to be able to see my calculator. So it's going to be 10,000. Hopefully you'll be able to kind of see it. I don't know why it's so hard to see. Second ln to get the e, and then 0.125. So $11,331.48. The more often you compound, so like if it's daily or continuously, the more money you're going to earn, right? Like the more often something compounds, because like compounding is you're earning interest then on your interest. So if it's doing it more often, it's going to grow quicker. So what we really didn't look at in this lesson at all was what happens if something like depreciates, like I mentioned, a car. So I would check out some of the extra practice and the resources for that. If you guys have any questions, please, of course, let me know. This is actually the last lesson of Unit 7A. So again, keep practicing, and thanks for watching.